All right, so these are some more limit comparison test examples. And so if you look at this problem, you got a plus on top and a plus on the bottom. So we know we're immediately going for limit comparison because we're not going to get a less than or greater than out of that. So our a sub n would be 2n squared plus 3n over the square root of 5 plus n to the fifth. And so the first thing to do when you try to pick out your b sub n to determine if it's convergent or divergent is you take the dominant parts. So on the numerator, that would be 2n squared. And then on the denominator, that would be the square root of n to the fifth. And then we simplify. And so this would be 2 over n to the 1/2. And so we know that the sum from n equals 1 to infinity, with a 2 outside, of 1 over n to the half, is divergent because our 1/2 is less than 1, which is our p, right? So our 1/2 is less than 1. Let's just write it the other way. Our p is less than or equal to 1. And there we go. So because that's divergent, now all we have to do is show that the limit of the two is equal to c. So again, we just rewrite our a sub n. We go over and grab our b sub n. And make sure you flip it. And then we distribute. So I'm going to move this down to give myself a little room. And I'm going to zoom in. All right. Shrink it. All right. So this equals a limit. And the easiest thing to do is just to distribute straight across. So we have 2 n to the 5/2 plus 3 n to the 3/2 all over 2 square root of 5 plus n to the fifth. Now at the bottom, that's 5/2 and that's 5/2. So that would be the best thing to do, is to divide everything by n to the 5/2. So we have limit as n approaches infinity of 2 n to the 5/2 over, and I'm just going to write it in at the end in green. So we have n to the 5/2, n to the 5/2, and then this is just n to the 5 because we already have the half as the radical. So that would be 5/2. See how that works? Just like that. So everything in the radical just is n to the 5. All right, so that cancels to make 1, that cancels to make 1, and we have the limit as n approaches infinity. In fact, we can already say that this one goes to 0, and that one goes to 0, just to make it a lot easier. And so it's just 2 over 2, which is 1, which is greater than 0. So by the limit comparison test, the sum from n equals 1 to infinity of 2n squared plus 3n over the square root of 5 plus n to the fifth is divergent. So again, that same basic idea. If our limit is equal to c of our a sub n and b sub n, and our b sub n is divergent, then our a sub n has to be divergent. And again, it's just applying these in a little bit of a trickier way. They both go together. All right, so now sometimes it's choosing a good b sub n as well. And so we already know, looking at this, we're probably going to be using the limit comparison. So our a sub n here is 1 plus 1 over n squared e to the negative n. So it works really well on getting rid of stuff. So if we were to write that limit as n approaches infinity of 1 plus 1 over n squared e to the negative n, you can already see that that n to infinity is just going to get rid of this. This is going to go off to 0, leaving us with 1 squared. So if we can get rid of e to the n, we're good to go. So if you come over here and we say our b sub n, which is our normal start, is to take and just go 1 over n squared e to the negative n, this would be 1 over n squared e to the negative n. And so plugging that in is going to make it not nice, but we just need to have a b sub n that works, right? So 1 over e to the negative n is what we can use. And if we rewrite this, this is 1 over e to the n. And so the sum from n equals 1 to infinity of 1 over e to the n is converging, again, because our r, our 1 over e, is less than 1. So our r here is less than 1. It converges. So now, if I take that b sub n and I plug it in here, right, See, I put the negative on it. Hold on. I got to get rid of that right there. Common error. Hold on. There we go. Now you guys, we're good. If I bring it down, I have to take the negative away. So I have e to the n and so on. Everything's good now. It's all kosher. All right, so 1 over e to the n can come in over here. And if we flip it, we get e to the n. And you can see those two now cancel. And so this would just equal 1. So by the limit comparison test, our sum from n equals 1 to infinity of 1 plus 1 over n squared e to the negative n is convergent. See, sometimes it's good to just pick an n. You don't have to pick the most dominant thing. You can pick something that will just work. So it converges, and it works at canceling and making that limit be 1. And we already knew it's going to converge because it's 1 over e to the n. So, all right. Now the last one is factorials. These are the fun ones. So you have to get creative. So whenever you see a factorial, the first thing you want to do is take your a sub n and write it out. See what you're going to get. So this is a 1 plus 2 plus, not plus, sorry, times 2 times 3 times 4, and so on, all the way to the n minus 2, n minus 1, and n. And on the bottom, it's just n to the n. So n, 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 dot, dot, dot. Let's get rid of that one right there. N, n, n. See, there are the same, since we have n factorial, we're going to have n factors. And n to the n means we'll also have n factors. So each of these will actually line up nicely. And so this would allow us to make the top bigger. So that would allow us to be a less than. This means we don't have to do the limit comparison test. This is just a plain old comparison test. And since we're doing this less than, we know we need to do converging. We're going to find some b sub n. Because I can change all of these to n's, as many as I want to. It's one of the tricks with factorials. If you have them all lined up like this, I can go, okay, well, 1, 2, 3, 4, as many n's as I want, but I know it's going to be n squared. I'm trying to show converging. So I'm going to just pick an n cubed. And to do that, then, it would just be 1 over 2, 1 over n, 2 over n, and 3 over n. So that would be 1 over n, 2, 3, right? And then I can make the rest of them just n's. See, these are all minuses in here. Every single one of them is a minus. So I can throw away the minus 2, throw away the minus 1, throw away the minus 3, and make them just n's. And what happens is they cancel. Let me put the dots in there too. Cancel, cancel, cancel. Even the dots cancel too. There we go. All right, so this would then become just 1 over 2, 3, and n. So we can say that our n factorial over n to the n is actually less than 1 times 2 times 3, which would be 6 over n cubed. And the sum from n equals 1 to infinity of 6, 1 over n cubed converges because our p is greater than 1. So if that converges, guess what? That one converges because we used a less than. So remember, this one is bigger, right? And so if the bigger one is going off to converging, so does the smaller one. So by the comparison test, the sum from n equals 1 to infinity of n factorial over n. I wanted to throw this in here to show you just don't always use limit on everything. If you can see something is just less than or just greater than, go for it. I also wanted to show you a factorial. So modifying the factorials with the minus 1 in there, you can always just use the less than to get rid of them. And if you need to remember why we're using that, you can go back to the first video or the second video and it'll explain why.